Okay, let's go ahead and get started with Chapter 5. We're going to look at probability distributions in both Chapters 5 and 6. So what that means is we're going to be combining our descriptive statistics from Chapters 2 and 3 and our probability from Chapter 4. And so the goal in statistics is to talk about what's probably going to happen. So what we're going to do is we're going to talk about random variables, and in Chapter 5 we're going to talk about discrete random variables, which means there are only so many of them. So for instance, if I open up a carton of eggs, a dozen eggs, and I want to look at how many are broken, that can range from 0 to 12, but it can't be 2.5. And then a continuous variable is one that can take any value. It's not just whole number values. And so an example of that is rolling a single die. And just FYI, vocabulary, one is called a die and the dots on the faces are called pips. So in Chapters 2 and 3, we talked about rolling them and collecting the data. In Chapter 4, we talked about the theoretical probability. The theoretical probability of any face on a fair die coming up is 1/6. And then in Chapter 5, we're going to make a model of that. And we're going to use the mean and the standard deviation to draw a model of our situation. So let's go ahead and talk about random variables. They're the numerical value of a random phenomenon. And we also often talk about them with capital letters. And a normal random variable is denoted like this. The n stands for normal, the mu is our mean, and the sigma is our standard deviation. And then we can look at a probability distribution that tells us what values that our variable can take and the probability that those values have. And so discrete variables are only whole numbers, like rolling dice, picking cards, the number of pets owned. I don't want to see someone who has 1.5 cats. The numerical day of the month. Even when it's past noon on the day, we don't say it's March 21st and a half. It's March 21st. How many days of class a person might miss in a face-to-face class. Then continuous variables can be along a range of values, like your height, your IQ score, your weight, your temperature, the time it takes you to travel to work or to school. And this is the example of a histogram. So the histogram would be used with discrete variables. When we have continuous variables, then we would have a density curve. And these are going to be the important equations for you, but don't panic because we're not going to use these equations very often. Now again, the round off rule is we're going to go one more decimal place than the number. So if our unknowns, our variables are integers, we round them to 1 decimal place. But there is an exception. If rounding hides some of the information, then we don't round. So for instance, in your book they talk about the probability that all 4 jet engines will work on a plane throughout the whole flight, and it comes out to be, the mean comes out to be 3.999999999. And if we round that, that rounds to 4, which says that all of the engines will always work, which isn't true. So don't round when it would change what you found with the data. Now, we're talking about identifying significant values. And so what we're thinking about here is that we have think of it as a number line. The mean is in the middle, and we're going to look at standard deviation units above and below. Well, when we get up here to standard deviation units, that is going to be the maximum not significant value. When we get down here 2 standard deviation units below, that is the minimum not significant value. So everything in between here is not significant, and everything above 2 standard deviations is significant. Everything below minus 2 standard deviations is significant. So significantly low values are below. So this would be significantly low, and significantly high values are 2 standard deviations above. This gives you a much better picture of what I just drew. And then what we're doing is we're looking for rare events. What we do in statistics is we come up with a assumption. And we're going to say, we assume this is true. Let's look at the data. And if we analyze the data and we get numbers that are improbable, the probability is extremely small, then the assumption that we made probably isn't true. So we assume with a fair coin that it's going to come up with heads half the time. But if we get 992 heads in 1,000 tosses, that means the probability we found was 0.992. That's very far from half the time. So if our probability, if our assumption is true, the 0.992 is very small, and it was a rare event. And because it would happen so rarely, we would say that 0.5 is probably not correct. Now, let's talk a little bit about statistics. A statistician will always use, I call them squishy words. These data suggest. This study suggests. They never say these data prove, this study proves. Prove is a definite word. We use things like suggest. And what we're doing in statistics is we're gathering evidence against a statement. And if we have strong evidence against that statement, we reject it. When we don't have much evidence against that statement, we fail to reject it. And we'll talk more about this in the next unit. So again, we're looking for unusual results. And if something is unusually high, we're looking at the probability that that or more will happen will be less than 0.05. If we're looking for something that's unusually low, we're going to look at the probability of that number or fewer will be less than 0.05. So 0.05 is our cutoff. Now, what happens is we call this alpha, and we set it up when we're doing a study, and we say that that's our cutoff point, and that works in social sciences. In other sciences, sometimes we set alpha to be 0.01. Sometimes we set it to be 0.001. So think about it. What 0.05 says, I'm willing to be wrong 5 times out of 100. What alpha of 0.01 means is I'm willing to be wrong 1 time out of 100. What an alpha of 0.001 says, I'm willing to be wrong 1 time out of 1,000. And so depending on the consequences of being wrong, we set these. In social sciences, 5 times out of 100 is pretty good. If we're going to be doing, let's say we're going to be doing a medical study and it's life and death, maybe we want it to be 1 time in 1,000 that we're willing to be wrong. Let's do a problem where we're going to look at this, and I am not going to do the examples that are in your textbook. Let's go back and let's look at problems at the end of the section. And instead of doing number 19, which you have the answer to. Let's do number 18. So this is on page 197. And number 18 is we're using the probability for significant events. Let's look at this one. And we're looking at 8 births and looking at the number of girls. And you can see we've done an observational study, or we could have listed, boy, girl. We could have listed all the probabilities and then count them up to see how much they would be. But what we're going to do is first the mean and the standard deviation. So that's number 14. So let's check that out. We wanted to find the mean and the standard deviation for those girls. So we want to go back to that formula I showed you on a previous slide. So we know the mean is the sum of our value times the probability of the value. So it's going to be, so I get a value of the sum at 4.059, and I want to round it to one more than the place value, and I'm thinking I may have made a mistake because it's supposed to round to 4. So on average, out of 8 births, there will be 4 girls. I'm going to pause and check my answers and see what I should have gotten. So here's my error. It should be 0.218. So let me change that. There we go. So this sum should be 3.996, which does round to 4 girls. Okay, so now I have that. So I know my mean is 4 girls. Let's calculate our standard deviation. All right. So our standard deviation is going to be, it's formula 5.4 on page 189. So my standard deviation, let's do this in a different color. So my standard deviation is the square root of the sum of x squared times the probability of x. Then we subtract the mean squared from that sum. Okay, so let's set that up. Okay, so this sum is 17.98. So now I'm going to take that sum minus the mean squared, which is 4 squared. So that's going to be the square root of 1.98. That comes out to be 1.407, and we round it to one place, so that would round to 1.4. And I believe that's the answer that they got in the back of the book. So we need those two numbers, that our mean is 4 girls and the standard deviation is 1.4 girls. Okay, so let's look at 18. It says find the probability of getting exactly 7 girls. So we want to do find the probability of 7 girls. So what are we going to do with that? We're going to go right to our table and we're going to find it. So it's going to be 0.031. And then for part B, what's the probability of getting 7 or more girls in 8 births? So that's going to be the probability of getting 7 or 8 in 8 births. So that's actually going to be the probability of getting 7 plus the probability of getting 8. So that is going to be 0.031 plus 0.004. I just got that over here from the table. And so that's going to be 0.035. All right, now it says which probability is relevant for determining whether 7 is significantly high number of girls in 10 births. The result from part A or for part B. I suppose it's this one because you've got more girls going there. I don't know. But the book says part C, the best answer is B. But let's look at D. That's what the most important thing. Is 7 a significantly high number of girls in 8 births? Okay. Is 7 a significantly high number of births? Well, let's look at our line here. Our mean is going to be 4. 1 standard deviation is 5.4. And 2 standard deviations is going to be 6.8. When we go low, which we don't have to in this because it's above the mean, but let's just do it for practice. This is going to be 2.6 and 0.2. So 7 is, okay, let's do this. 1 standard deviation, 2 standard deviations, minus 1, minus 2. So remember, our significantly high or low will be outside of 2 standard deviations plus or minus the mean. And 7 is over here. So yes, this is significant. Because well, it's beyond 2 standard deviations, we can say that, but we can also say that the probability is less than 0.05. So 2 reasons there. Let's talk about expected value now. Expected value is the outcomes we can expect. And you can see in your book, example number 6, it talks about betting. But what I want to do, let's just talk about our formula. Expected value is the value times the probability for all the probable outcomes, and then we add those together. So let's look at, and I don't want to do number 27, I would like to do number 30. So we're looking for life insurance. So the probability for a 50-year-old woman to live in a certain year is 0.9968. So the probability that she's going to live all year is 0.9968. Now, she is going to buy a $50,000 policy for $226 for the year. Okay. Now the question asks, from the perspective of the 50-year-old female, what are the values corresponding to the 2 events of the year, surviving and not surviving? So we know that when she survives, if she survives, she's out $226. So the value of surviving is going to be that she loses the amount equal to her premium. Her value of dying, well, if she dies, she's going to get $50,000, but she had to pay the $226 premium. So that value is going to be $49,774. Okay? Now, part B says, what is her expected value? So here are her two values. What's her expected value? Well, the probability of her surviving is, so our expected value is the value times the probability. Let's say the value of our event times the probability of our event plus the value of the other event times the probability of the other event, so on and so forth. But she only has two possibilities. If she survives, it's going to cost her $226. That's the value, but the probability is 0.9968. If she dies, her value is $49,774, but the probability of that happening is 1 minus this. So that's going to be 0.0032. So this is going to be $159 and some cents. And this is going to be a minus $225 and some cents. And that comes out to be about $66. It's actually $66.41, but about $66. So what does that mean? That means that the 50-year-old woman is going to lose $66 if she lives. You know, is that pretty good in case she would happen to die? Now, what is the value to the insurance company? Well, if she loses $66, the insurance company is going to gain $66. So that would be the profit if it sold many, 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 many policies of that value. And insurance companies do have people who calculate the probability of someone of a certain age with certain habits dying in a year, and that's how they do calculate the premiums for life insurance policies. So that brings us to the end of 5.1.